Alice, Bob, and Eve explain quantum variational eigensolvers.
I love jigsaw puzzles, but this one is hard. I've been trying to find the piece that fits perfectly here, but there are so many possibilities.
You know, your puzzle-solving strategy reminds me of quantum variational eigensolvers, or QVEs.
Oh, QVEs. That's a perfect analogy for what you're doing, Alice.
How is solving a puzzle anything like quantum computing?
Think about what you're doing. You're trying to find the piece with the minimum energy that fits perfectly in that space. In quantum chemistry and physics, we often need to find the lowest energy state, the ground state of a system.
Classically, we'd have to check every possible configuration, which gets impossibly complex for quantum systems.
So how does a QVE help?
It's like having a helper who can try many pieces simultaneously. A QVE uses both quantum and classical computers working together, a hybrid approach.
First, we make an educated guess about what the solution might look like. We create a trial wave function with adjustable parameters.
Like how I start with pieces that seem promising based on color and shape?
Exactly. We prepare this guess state on a quantum computer using a parameterized quantum circuit.
Then we measure the energy of that state. The quantum part is good at this step, estimating the expectation value of our Hamiltonian.
Then comes the classical part. Based on the energy measurement, a classical optimization algorithm adjusts the parameters to try to find an even lower energy state.
Like how I might rotate or try different pieces based on how well the previous one fit?
Precisely. It's an iterative process. We keep preparing new quantum states with updated parameters, measuring their energies, and adjusting until we converge on the lowest energy state.
What makes this approach powerful is that it can work on the noisy, intermediate-scale quantum computers we have today. We don't need perfect qubits or error correction.
So it's like finding the solution through educated trial and error, but using quantum parallelism to evaluate many possibilities at once?
That's it. And it's particularly valuable for chemistry problems. Finding the ground state energy of molecules could help design new materials or drugs.
The beauty is that it divides the work. Quantum computers handle the hard exponential scaling part of preparing and measuring quantum states, while classical computers do the optimization they're good at.
So my puzzle solving is like a human version of a quantum classical hybrid algorithm. That's rather poetic.